We're now beginning the last chapter of the first calculus course. Up until now, we've talked about the rate of change, the slope of a line, of a curve, any curve at any given point. We used it to find the extrema points, the maximum minimum points, the vertices, and how to find concavity, the bends of the curve. Now we're going backwards. We're going to find now, given any function, in a closed finite area, we're looking for the area under that curve between our bounds. In calculus 2, we're going to take this further and then we're going to take this thing and rotate it about an axis. Then in that case, we'll be finding the volume of this object. But that's in calculus 2. Right now we have to learn how to crawl before we can walk, before we can run. Like the derivative, we defined the derivative of a function as a limit as h goes to 0 of our difference quotient. Now, why is it a limit? Because what we're doing here is we're looking at different iterations as h, the distance between our test value and our actual value gets closer and closer and closer and closer and closer. When we deal with integrals, we will also use the limit. To better estimate the area of a function above the x-axis and between two bounds. I'll define that all in a little bit. Well, maybe not get to that point, but we'll definitely get there tomorrow or the next day. So the integral will be used to, we'll use the limit function because what we want is we want more and more and more items to calculate to approximate the solution. So the goal of an integral is to approximate the quantity we're going to look at area Well, all right, the goal of an integral is to approximate the quantity of a function by dividing it up into smaller regions. Each each of no, each of which we can approximate by some simple algebraic operation. Basically, if you think about it, we're going to talk about an area. How do you find what's the formula for area of a regular equation of an object? Yeah, length times width or base times height. So let's look at the first one, an example. We have a rectangle. Let's make it 2. How would you calculate the area of this rectangle? The base is 2 and the height is 1. So we know that the area is 2. But we're going to use the same concept now, but with more uneven functions. Because this one's pretty straightforward since it's a constant rate of change and everything. But let's look at this. If we cut this into 2 pieces, what's the area of the first piece? The width is 1 and the height is 1. What's the area of the second piece? The width is 1 and the height is 1. So we get 1 plus 1. The total area is the sum of those two. We're back to being 2. Add those together. Okay, what if we're going to cut each of those into halves? So this is 1/2, 2/2, 3/2. So now we have 4 areas to calculate, together which will give us the actual area of the object. So we have here the base. Notice how the base is uniform. So we know that the base for each one of these now is 1/2. And also the height is 1. So the formula for our equation, base times height, is 1/2 times 1. That's for each one of these. So this is 1/2 times 1 plus 1/2 times 1 plus 1/2 times 1 plus 1/2 times 1. Add those all together and we get the area. So we have 1/2 times 1 is 1/2 plus 1/2 plus 1/2 plus 1/2. Half plus a half is 1. Half a half is 1. So again, we see the area is 2. So we keep on going. What if we cut those in half? We keep on going. We cut those in half. So what we're looking at here is this. The area is the sum of all, I'll call them subareas. So it's area 1 plus area 2, dot, 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 plus area n, depending on how many we have. So since it works for a rectangle like that, we can presume it's going to work for any object that we have. But that's the problem. Not all functions are that straightforward. Example, what if we had our function of 1 minus x squared and we went on this interval? What does this function look like? That's what, make it 1 squared. That's too easy. Make it 1 squared. Actually, I should have left it as that. Oh well, we'll do this one. So we're going from 0 to 1. That's my domain. When x is 0, y is 1. And when x is 1, y is 0. Since it's a quadratic equation, we know it's a curve. It's a parabola opening downwards. Shift it up 1 space. Now, as you see, we can't make those little rectangles like we had over there. So our objective is to find the area of the curve f of x. So how do we do that? Well, can we do what we just did? The base is 1 and the height is 1. Does it equal 1? No, because if it was 1, it would look like this. So that's too much. How can we fix that? So let's cut this in half. Now we have another problem. We have the concept of circumscribed or inscribed. Circumscribed refers to the outer area. Inscribed is the inner area. What I'm getting to is this. If we cut this in half, our x-axis, our width, the base. Now, what the circumscribed means is we're going to take the area of. So now we're going to look at rectangles. We're going to keep this model available because the area formula we have, base times height, defines a rectangle. So we're going to keep that model. So the first model we have well, no, let's do that one. Let's start from here. Let's stay inside the area. Because I want to have this one less than or equal to the true area less than this one. So since I cut this one in half, I have to use that point. This is my rectangle for the first one. So notice I have my sub interval here from 0 to 1/2. And then I have another sub interval from 1/2 to 1. Remember, and this point right there is of the function 1 minus 1/2 squared, because our function is 1 minus x squared. That's our equation. So this value here, the height of our rectangle is 1 minus 1/4 is 3/4. What's the width? Or what we're looking for is what is our delta x? Between 0 and 1/2, it's 1/2. So what's the area of this curve, of this rectangle, of this first one, A1? Base, which is 1/2, times height, which is 3/4, which makes it 3/8. That's only for the first one. Now, if I use because out of my intervals, I'm using the right and side. So notice, since the function's decreasing, if I use the right endpoint, am I going to get the maximum or minimum value? In other words, is it going to be bigger than or lower than the graph itself? The graph, I have extra space here, so I'm going below. Since it's decreasing and I'm using the right hand limit or point, I'm going to find the minimum here. Because this value here, once I add these two areas together, I'm going to have the minimum value of my area. So the second interval right here from 1/2 to 1. Again, the width is 1/2. That's delta x. What's my height from this point? 0. So it's 0 times 1/2 is 0. The area of this bottom part is 3/8 plus 0 equals 3/8. So that's my lower estimate. Remember, the whole concept here is we're trying to approximate. Yeah. As it says here, the goal is to allow us to approximate some simple algebraic operation. we're approximating the solution. Why? Because remember, these are functions that curve. We don't know the true value of it. We can only approximate what we get. So then we have the real, whatever the real area is. Now let's go to the upper area, the maximum part. In this one, we're going to use the left endpoints.
What do you mean by left and like right endpoints?
You see my intervals. My
Yes.
intervals are from A to B to C.
Yes.
In this first interval, the left endpoint is A, the right endpoint is B. In this next interval, the left endpoint is B, the right endpoint is C.
Yes.
So that's what it means, left and right endpoint.
Okay.
So in an interval, if we're looking for the minimum aspect, we want the area to be inside the graph itself,
Okay.
when it inscribed. So in this case, we chose the right endpoint because it'll give us a rectangle inside there.
Okay.
And because we use the right endpoint from this point, the area is zero. Now, from here, my right endpoint for this first one, this is A1, this is A2. So the height, my right endpoint, the height is 1, and my width is 1/2. And then the area of the second rectangle, the height at 1/2, the value here, so we have to plug that into our function. So we have f of 1/2, 1 minus 1/2 squared, 1 over 1/4 makes it 3/4. So this value is at 3/4. Times the delta x, which is 1/2. Remember, our formula for area is base times height. The base is the width of this thing, and the height is where it goes to touch the graph. So we have 3/8. So the true area is, I add both of those together. So A1 is 1/2. A2 is 3/8. Add those together. I need a 4/4, so it's 7/8. So I know, again, remember, we're approximating the area of this rectangle or this curve, the function. We know the true area of it has to be between this lower sum and this upper sum. Okay, why do I call it upper sum and lower sum? How do we find the area for the upper number? We added A1 plus A2. So the right-hand number is made up of adding up those two numbers. So it's the upper sum. The lower sum is made up of adding these two numbers together. Let me give a better diff. So in this case, when we say upper sum, oops, We're talking about the maximum value, and it's the larger estimate. That's the upper sum. The lower sum is the minimum value. It's the smaller estimate. So far, so good. So how do we find in our example? In our example, how do we find the upper sum? For the upper sum, we'll take it, or we have to find rectangles. We want the rectangle so it encompasses that curve. So that would be an upper sum. It's upper because we have all this area here is extra. It's you call it like a buffer, like a safety zone. And the lower sum will be given inside the function because we're missing this part. So you could also say that upper sum is an overestimate, lower sum is an underestimate. Because what we're doing is we're trying to, and how do we make that better? Because remember, our upper sum, what were numbers? Our upper sum was 7/8, and our lower sum was 3/8. Can we make our values closer together? How? Making more rectangles. Yes. So for the lower sum, instead of just 1/2, let's cut it into 4 spaces. This is our lower sum. This is our upper sum. Because we're going to know that our area is somewhere between there. And it's very important that you have to look at the graph first, because will the lower sum always be the right endpoint? No. It just so happens, since this is a decreasing function, that means our lower value is to the right. So for this first one, we have to find the area of the height at 1/4. That's this one. Then for the next one, we need to find f at 1/2. That's this one, because I want this rectangle. And then for the third rectangle, I want it at 3/4. And then the last one, f at 1. So because it's a decreasing function, out of my intervals, I'm taking the right endpoint. And these will give me my height values. My width, the base part, they're the same. They're all delta x's. How do I find delta x? How would you find delta x if you had to give it a formula? Because remember, all of these have to be the same size. For right now, they have to be the same size. Well, remember, we have a beginning and an end in our domain. So to find the delta x, we find the difference between two numbers and divide by how many we want. So in this case, what is my delta x? How wide is it here between 0 and 1/4? 1/4. How far is it 1/4 to 1/2? 1/4. These are all the same size. They're all 1/4. Just think about it. If this is 1/4, 1/4 plus 1/4 is 1/2. 1/2 plus 1/4 is 3/4. 3/4 plus 1/4 is 1. So all of these are the same width. So A is 0 and B was 1. So we have 1 minus 0. I want 4 areas. So delta x is 1/4. Because I wanted 4, this tells you how many intervals I want. So to find the area, we have the height, which is our function, times delta x. And delta x is constant throughout all of them. So let's look at this one. Next page. Let's try to find the area of the lower bound.
And will they always be the same differences in uh, distance, or could the lines be like uneven or non-symmetric?
How do you mean?
Like here, it's like zero. We like divided it up evenly among each sides, and you
Yes.
could it ever be where it's like uneven, like 1/4 to 3/8?
Yes, yes, yes. But for right now, we're introducing basic concepts we're developing there.
Okay.
Okay, since this is a lower bound, I'm using my x values. The x values I'm going to use are 1/4, 1/2, 3/4, and 1. Because I have to use the right endpoints of each of these rectangles. Here's A1, A2, A3, and A4. The function that we are using is that one. So the first one, this is my x1, this is my x sub 2, this is my x sub 3, and this is my x sub 4. So at 1/4, we have 1 minus 1/4 squared, 1 minus 1/16 is equal to 15/16. So area 1 is the height is 15/16 and the width is 1/4. Let's find the second one. So f at x2. This is x1, this is x2, this is x3, and this is x4. So x2 is 1/2. 1 minus 1/2 squared is 1 minus 1/4 is 3/4. So the second rectangle is 3/4 times 1/4. Then the third one, f of x3. My third x is the 3/4, which is 1 minus 3/4 squared, 1 minus 9/16, which is 16 over 16 minus 9/16, which is 7/16. So third one is 7/16 times 1/4. And the fourth one, which is f at 1. 1 minus 1 squared equals 0. Zero times 1/4. So it's 15 times 64, 3 times 16, 7 over 64, 0. So we have 15 divided by 64 plus 3 divided by 16 plus 7 divided by 64 plus 0. So the area of A1 plus A2 plus A3 plus A4 is 0.5315. That gives us our lower sum. We do the same thing now for the upper sum. But what changes now? We have 4 intervals. Since we want the upper sum, which means now we have to overestimate. So do we use the left or right endpoint? We have to use the left because we want to include the entire graph. So my x values I'm going to use are the left ones. It's 0, 1/4, 1/2, and 3/4. So again, my delta X is still the same. It's 1/4 for all of them. So that's my base. All I have to do now is calculate what my height is. So 1 minus 1 squared, or 1 minus 0 squared is 1. So this is from my first one. This is f of 1. The next one is at 1/4 for this next. So this is area 1. That's with f of 1. Area 2 is at 1/4. 1 minus 1/4 squared. Well, I did that up there. It's 15/16. The next one is f at 1/2. 1 minus 1/2 squared. I did that up there. It's 3/4. And then f at 3/4. 1 minus 3/4 squared. That was 7/16. So the area is 1 times 1/4 plus 15/16 times 1/4 plus 3/4 times 1/4 plus 7/16 times 1/4. All right. So for the first one, I get 1 divided by 4 plus 15/64 plus I missed the type of, so it's 1/4 plus 15 divided by 64. Much better. Plus 3 divided by 16 plus 7 divided by 64. This one equals 78125. So when we cut it in two pieces, the lower sum, the area, and upper sum. The lower sum in the first one was 3/8 and 7/8. So 3 divided by 8 is 0.375. And 7/8 is 0.875. When we cut it into four, four intervals, we got what we just found. We found 0.5315, and the upper bound was 78125. So what do we notice? It's getting closer and closer and closer. So if we had 16, or if we had 1600 intervals, eventually it would approach the true area under that curve. Okay, right now you see it's pretty lengthy, time expensive and everything. But is there another way we could try to make this even faster for us with what we know so far? This is what we have so far. Um, so we have the inscribed and we have the circumscribed. How about because up until these, and these we had to use the right endpoint or the left endpoint. What if we use the midpoint value? If we use the midpoint value, then our rectangle, it'd go up there. Our midpoint values, you see what would happen to them? Maybe it's easier if I show you in two spaces. If I chose the midpoint between these two intervals and made my rectangle according to those, what do you notice? It's both circumscribed and inscribed. So what you're missing here, you have too much here, that will limit how much wasted space we have by using midpoint values. Okay, so half this, we took this first one, we took it from two spaces. So when we're going to use 1/4 and we're going to use 3/4. So the true area, the midpoint area. So the first one is f of 1/4 times 1/2, because that's still the width of it, plus f of 3/4 times 1/2. F of 1/4 was 15/16 times 1/2. And f of 3/4 is 7/16 times 1/2. So we have 15 divided by 32 plus 7 divided by 32. 0.6875. So when we divided it in two, the midpoint area gave us 0.6875. That's a lot better than these other ones because we know that these are approaching, it's 0.5 here, 0.7 here. It's going to be 0.6 something. So we're automatically getting much better results if we use the midpoint. Let's try when n equals 4. Yes. What does that have to do with it?
Because I need a title so I can go back to my notes.
Put section 5. Okay, I'll stop class so you can know what it is.
No, you stop.
It's areas and estimating the finite sums. You have the packet I gave you last week. Think twice. That was the important question you had. So now we're looking at cutting it into 4 spaces. So the midpoint here is 1/8. This is the one we're going to use for this first one. So f of 1/8. Then we're going to use 3/8 is the next one. Then we're going to use 5/8. Those are all my midpoints between all these intervals. Then I'll look at 7/8. So I'm looking for this area, this area, this area, and this area. The function is still the same. 1 minus x squared. 1 minus 1/8 squared is 1 minus 1/64 is 63/64. 1 minus 3/8 is 1 minus 9/64. 55/64. 1 minus 5/8 squared. 1 minus 25/64. 39/64. 1 minus 7/8 squared. 49/64. 25/64. Times the interval size, which is 1/4. And add up all those will give me the area. So we have 63 divided by Geez, 64 times 4. 256. Plus 55 divided by 256. Plus 39 divided by 256. Plus 25. Equals 0.7109375. So at 4, we got 0.6875. We do 4. At 4, it's 0.07109. So it's getting, using the midpoint formula is a lot more economical. All right, so let's look at another example. Yeah. So what's really happening? The true area is made up of what? The function times the width. This is the height, and this is the width. Where delta x is made up of b minus a over n. And instead of x, you can use the midpoint, or you can use the upper lower sums. Where c of x is the midpoint. And what does that look like? F of C1 delta x plus F of C2 delta x plus F of Cn delta x. Of course, the more n, the larger your n, the more accurate it becomes. And okay, as we did with derivatives, we started off with very lengthy, work-intensive formulas. We'll do the same thing with integrals. We're doing the algebra part of it now. Later on in this chapter, I'm going to show you shortcuts that'll do away with all this. They'll make it much easier for us to work with. Besides area, we can determine distance traveled, overall distance traveled. Because if the velocity v of t is known, we can find the distance traveled. How can we do that? If we know the velocity, then all we need to know the distance traveled is what? The intervals, beginning and the end. So all you need to have is the beginning and end time period. What is velocity? How do we calculate velocity? Remember chapter 1, how do we find, or chapter 2, how do we find, what is velocity? How do you find it? First derivative of your position function. You figure that kind of secondary nature, you should know that. Why do you need to know the position function? Because the position tells you I started at point 1, I moved to point 2. There's a distance there. So how do we find the, if I give you the velocity, how do you find the position function? If given that, what's that? Nope, wrong way.
Taking the antiderivative
How do you find that?
by going backwards.
How do you find that? We haven't talked about that yet. We haven't defined any formula for it. What is the antiderivative? Again, you can't read ahead. If you do, knock yourself out. But I need to show you where it's all coming from. Because the velocity is a derivative of your position function, that means we can find some function that represents our position function plus a constant. Why plus a constant? Because if our position function was that, then the derivative of it, the constant would disappear, which would give us the velocity. So we have to do is find a value, a function that when we take the derivative of it, it will give us the velocity. So that f prime of which equals the velocity. Why do we need to know this? Because velocity is the change of distance, the change of position over change of time. Position, distance is relative to position. So pretty much the displacement function, the S function, tells us if we start here and go here, if S1 is here and moves to S2 here, we can measure and find out the distance from there. How? Distance is S2 minus S1. Because the position functions, locations tell us that. So how do we represent S2 and S1? Well, they're relative to our intervals. On some interval AB, S2 minus S1 would be S of B minus S of A, which is the same thing of our function that we found. Okay, that's all great and good. If velocity was constant, it would be great. But what if from velocity at 0 to velocity at 1 to velocity at 2 to velocity at 3 to velocity at 4, you notice how it doesn't have to remain constant all the time. For example, when you're on the highway, do you always remain the same speed everywhere you go? No, of course not. Traffic slows down, or if you see an opening, you're in a hurry to get there, you'll take it and go. So what happens here? So if we can break these things down to smaller intervals where we can keep the velocity constant in that interval, then we can further take it down to the S function, the displacement function, and find the true distance traveled. So again, why is this important? Because what do we do with the 1 minus x squared function? To approximate the true area of that, we broke it down to smaller pieces. To find the true distance traveled, we break it down to smaller pieces and do what with all these small pieces? We add them up. Subintervals. Because what your objective is, try to make your velocity constant. Create smaller subintervals so the velocity is constant. Because once you can do that, then we can figure out the position function. Then we can find the rate. Then distance equals rate times time. What is rate? Rate is S of B minus S of A over B minus A. It's the rate of change. Let's look at an example. I'm sorry, here you go. I'm sorry. So let's look at this example. Example 1. Well, so the true distance is equal to and so on and so forth. And that's only possible is if we can find a constant velocity so that each one of these intervals in our time intervals, it remains constant. Because if it's changing, if it's increasing or decreasing, then we can't use it to any level of accuracy. So. Example 1. It says the velocity function of a projectile fired straight up into the air is f of t equals 160 minus 9.8 t meters per second. Use the summation technique above to estimate how far the projectile rises during the first 3 seconds. How close do the sums come to the exact value of 435.9 meters? Remember, it says use the summation technique we just did. That's the one that D equals VT1 delta T plus VT2 delta T dot 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 VTN delta T. That's the one that we're supposed to use. So our velocity function is our function given, 160 minus 9.8 t. How do we know it's not acceleration? How do we know this function is not acceleration? Acceleration is a second derivative, so it'll have been squared. We had meters per second squared. All right, so what do we know here? Our time intervals. For our x-axis. And we put it down here. This is T0, T1, T2, T3, and so on and so forth. Because we're only going 3 seconds. So we can say this is 1, 2, 3. Similar to our last example. What happens when this object takes off? What happens to the velocity at each second? Let's see. When t is 0, what's our velocity? We have 160 minus 9.8 times 0. What does that equal? 160. When time equals 1, 160 minus 9.8 times 1. What is 9.8 times 1? 9.8. So 160 minus 9.8 is 150.2. What is it at 2 seconds? 169.8 times 2. So we have 160 minus 19.6. 140.4. Yeah. And then at 3 seconds, 160 minus 9.8 times 3. 29.4. So what do you notice about our velocity? It's decreasing. Why? If it's shot straight up, what's the constant force acting upon it? 9.8 is gravity. So the longer it stays up in the air, the more force gravity is acting against it. All right, so those are all of our function velocities. What's our delta t? Well, we're going from 0 to 1, so delta t is 1. So if we add up all of these, what do we get? So we get 160 plus 150.2 plus 140.4 plus we don't use that. Minus 1. Because think about it. What we just did here, this interval went from 0 to 1. That's 1. Then we went from 1 to 2. Then we went from 1 to 3. So we first add up these 3, which gave us, what was that number? 450.6. What happens if we use the upper numbers, these numbers? So we have 150.2, 140.4, 130.6. $130.6 plus 140.4, 150.2. Then it's 421.2. So if we started off at 0 and used the left endpoint, that gave us a larger number. So this is our upper sum. If we use the right endpoint, this is our lower sum. So what we're looking for here is how far do we get to our, so it's asking us how close did we come to the exact value of 53? Exact equals 435.9. Okay, so this is the first part, saying use the summation technique to describe how far the projectile rise after the first 2 seconds. So after the first 3 seconds, it went 450.6. Why can we not use this one? Because it really started, if we use the lower endpoint, here's the first travel, here's the second travel, here's the third travel. So that's what we did there. All right. Then it asks us, how close did the sum get to the exact value? And, oh no. So our calculated value, which one's closer? So we have 450.6 minus 435.9. That's 14.7 as opposed to 435.9 minus 421.2. Ooh. So both of these are 14.7 meters away. Why? Why are they both 14.7 meters away? Because the velocity is constant, and we took the delta x to be the same with all of these. So whether we take it in the lower bound or an upper bound, since the only force acting upon it was gravity, from the upper sum to the lower sum, it's going to be the midpoint. Because there's no other acting point. It's straight up, straight down. Now, how can we improve it? instead of having three intervals, what if we cut them in half? What if our delta t was divided by 2 and we had 6 intervals? Or if we had 12 intervals? So what we're looking for is we're trying to approximate how close it is to our exact value, which is what it's called the error magnitude. The error magnitude is how far, it's a distance, a numerical distance, how far your estimated value is from your exact value, what it's supposed to be. And why is it absolute value? Right. Well, yeah. Because if you think about it, it's always the second x2 minus x1. So in this one, x2 is 450 minus that, as opposed to this minus 421. So if we look at the distance, we always want to be positive, so we don't even worry about it. So that's the exact magnitude. Again, the exact value, we don't know how to find yet. All we can do is find our calculated, our estimated values that we came up with. And then from there, you can calculate your error percentage. Your error percentage is your error magnitude divided by the exact value or the true value. So we're looking at the error percentages as a ratio. How far is your difference away from the true value? Okay, displacement versus distance traveled. What's the difference? You ever hear of displacement? You probably have. If you heard the story of who discovered that? Dang, now I forgot his name. But the guy who discovered the weight, the true mass of gold by saying Eureka, Euclid. But he was the king asked him because he had somebody make a crown for him with a whole bunch of gold, and he asked Euclid, "Is this true? What he gave me, is that my gold I gave him? Is this a true gold?" I said, "How do I figure that out? By displacement. If you take that amount of gold, put it in the water that goes out will displace with whatever the true mass that's inside there. That way you can figure out, is it a true gold or is it gold or is it lead? Because they have different densities, they'll displace different amount of water. He figured this out by taking a bath. He saw the bathtub was full to the top. He stepped in, the water left out. When he stood up, said, oh, that's how much volume my body takes. So that's what he figured out. So that's displacement. How much is different from the original value? What is distance traveled? The difference is this pretty much. The distance traveled, if I started here from point A and traveled to point B, let's say it's 1,000 miles, and traveled back How far did I travel? Yeah, the total distance traveled is 1,000 plus 1,000 is equal to 2,000 miles. So that's distance traveled. Displacement, on the other hand, is now you have to put values on directions traveled. So going from point A to point B, that's going to the right, so we'll call that positive. That's a positive 1,000 miles. But going back from point B to point A, it's going to the left, so we'll call that negative. So how much displacement do I have? 0. I have 1,000 minus 1,000 is equal to 0. That's the difference. In physics, if you picked up a 1,000-pound boulder and put it back down, how much work have you done? Nothing, because it's displaced amount of work. Your first work is you picked it up. It's a positive force. And then when you put it down, there's a negative force. So the work overall zeroed out. So that's what this part's looking at. So how do we figure this out? Distance traveled you use the absolute value of t of the velocity. As opposed to this one, it's just delta t plus or minus the next one. So with displacement, you have to allocate a sign in direction. Gravity pulls down, so it's going down as negative. Explosion goes up, so it's positive. So you can know what is your exact displacement? It's the difference of the two. As opposed to the total distance traveled is you add up all the individual locations. Crikey. I don't want to do that, but I'll do it. So let's look at this example. Oh, no, it's past 1 o'clock. We'll pick up from here next time. We're going to do example 2 next time. Yeah, we're not too far from being done with this. Today's Thursday, isn't it? Oh, go have a weekend. I said we'll see you tomorrow. No, I'll see you Monday.